We're going to use the definition of derivative to come up with formulas so that we don't have to use the definition of derivative every time we want to find the derivative of a function. Remember that the definition of derivative is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Let's consider a constant function f of x is equal to c. If I want to differentiate, I'm going to find the limit as h approaches 0 of, when if f of x is equal to c, then f of x plus h is also equal to c. It's a constant. So I have c minus c in the numerator, and that's going to be 0. It should make sense. If we think of a constant function, horizontal line, and the derivative as giving you the slope of a tangent line at any point, rise over run, there's no rise for a constant function. Slope is 0 everywhere. Cool. Now, what about a linear function f of x equals mx plus b, or a quadratic function f of x equals x squared, or a cubing function f of x is equal to x cubed? What I'd like for you to do is use the definition of derivative to find the derivatives of each of these functions. Come back when you're done. Now I've got a lot on the screen, and feel free to pause it and check all the details if you like, but for the linear function f of x equals mx plus b, we end up with f prime of x is equal to m, and that should make sense because it's the slope of the line. For f of x equals x squared, we end up with 2x. So f prime of x is equal to 2x. That makes less sense. We'll just move on. F of x equals x cubed gives us a derivative of 3x squared. So f prime of x is equal to 3x squared. Now math people look at patterns. If you notice, looking at the quadratic function f of x equals x squared, that 2 is the exponent of x, and we have a coefficient of 2. The exponent of x becomes 1. We didn't write it, but there it is. For x cubed, the exponent is 3. That becomes a coefficient 3. And then the exponent is 2. So it seems like the exponent is dropping by 1 each time, and the exponent is becoming a coefficient each time. Does that apply for the linear function? It does, as a matter of fact. The exponent had been 1. 1 comes out front, and then we have x to the 0. What about the m hanging out here? We'll come back to that in a bit. This leads us to draw a conclusion, right? So suppose we have f of x is equal to x to the 4th. If you had to guess what its derivative would be, what would you say? I'm thinking the 4 comes out front, drop 1 from the exponent, the answer would be f prime equals 4x cubed. And that actually turns out to be the case. If we look in general, so let's just consider f of x is equal to x to the n. Then f prime of x is equal to the limit as h approaches 0 of quantity x plus h to the n minus x to the n divided by h. We can expand the first term in the numerator as using the binomial theorem. We have the limit as h approaches 0 of x to the n plus nx to the n minus 1 h plus, now if you check out the binomial theorem, you know the rest is a bunch of stuff that all have at least h squared in them. I'm going to move on. Minus x to the n, right? That was the last term in the numerator, all divided by h. Continuing on with this process, we end up with the limit as h approaches 0 of the x to the n's subtract out. Now, I have an h in the first term, I have h squared in all the rest of the terms, and so I can factor out an h. And I'm left with nx to the n minus 1 plus a bunch of stuff that all has h in it. Now, the h divides out in the numerator and denominator, and then when I apply the limit, all the stuff with h goes to 0. As a result, what I have is n x to the n minus 1.